As we've seen in a previous video, solids and fluids are very different. A solid keeps its shape, so it's possible to take a piece of a solid and do whatever you want with it, such as applying forces. We can't do that to a liquid or a gas. They must be contained in vessels. So it's very important to know their physical properties, especially those related to their volume and surface. We'll see two of them related to their volume, density, and others related to it, and specific heat. In another video, we'll see two others related to its surface, viscosity and surface tension. Let's start with the density. It is the relationship between the mass m of a body and its volume v. We use the notation ρ to identify it. Here are the densities of some fluids that are important in our professional activities, as used in practice. For liquids, temperature variation has a small importance in their density value. In this table, we can see that the water density varies only 1.2% from its maximum value at 4 degrees Celsius to its value at 50 degrees Celsius. For gases, the situation is not so simple. Their density varies a lot with pressure and temperature. We'll see this matter in other videos, especially concerning what happens in the atmosphere. But here is a table containing the values for some gases when the pressure is 1 atmosphere and the temperature is 0 degrees Celsius. In some cases, density is called volumetric mass density or specific mass. Chemical engineers use this latter expression only for pure substances, but civil engineers use it almost as a synonym of density. In fact, specific mass is the term that they prefer. That's because they save the term density for relative density, which is the relationship between the density of a fluid and the density of a substance taken as reference. In the case of liquids, water at 4 degrees Celsius is the reference, and in the case of gases, air at 0 degrees Celsius and 1 atmosphere is the reference. In many cases, the term specific gravity is used, especially for liquids. Here are the relative densities of some liquids, and here are the relative densities of some gases. The relationship between the weight W of a body and its volume V is what we call specific weight. We use the notation gamma to identify it, but W equals mg, thus gamma equals mg over V. So gamma equals m over v g, or gamma equals rho g. Knowing this, we get delta equals rho over rho naught equals rho g over rho naught g equals gamma over gamma naught. The specific volume is used extensively in thermodynamic studies. It is the inverse of the density of the material. So, the specific volume of a substance is the ratio of its volume to the corresponding mass. It's used especially for gases. Most of the time, values are given at standard temperature and pressure, STP, which is 0 degrees Celsius or 273 Kelvin and 1 atmosphere. Here are the values for some gases and for some liquids. Specific heat is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. The units of specific heat are usually calories per gram per degree Celsius or joules per gram per degree Celsius. Water has a high specific heat. We'll see in other videos how difficult it is to vary water temperature. Here are the specific heats of some common substances, so you can compare them to water. Note that 1 calorie equals 4.18 joules. In this graph, we can see the water-specific heat variation with temperature from 0 to 100 degrees Celsius. Also, ice has a high specific heat. For this reason, liquid water and ice play together an important role in the thermal equilibrium of planet Earth. In the case of gases, there is the specific heat of a gas at constant pressure. It is defined as the quantity of heat required to raise the temperature of unit mass of the gas by 1 Kelvin, keeping the pressure constant during heating. In this table, we can find some Cp values for common gases. Also, there is the specific heat of a gas at constant volume. It is defined as quantity of heat required to raise the temperature of unit mass of the gas by 1 Kelvin, keeping the volume constant during heating. In this table, we can find some Cv values for common gases. These two parameters are very important when we study the relationships between pressure, volume, and temperature in gases. Okay, let's solve some problems. Here is an oil sample. Its volume is 7 cubic meters and the corresponding mass is 6,300 kilograms. So, its density ρ equals m over v will be 6,300 over 7 equals 900 kilograms per cubic meter. As it's a liquid, for the calculation of relative density or specific gravity, delta equals ρ over ρ naught. The reference will be the water, so ρ naught equals ρ H2O equals 1000 kilograms per cubic meter. Thus, it will be equal to 900 over 1000, 0.90. The specific weight will be gamma equals W over V equals mg over V equals m over v g equals rho g. Let's assume that g equals 9.8 meters over square second. So the specific weight will be 900 times 9.8, 8,820 newtons over cubic meter. The specific volume will be Vs equals V over m equals 7 over 3,300 equals 0.0011 kilograms over cubic meter. Now another problem. We'll drop some amount of liquid water which is in a plastic bag from a height h. Let's assume that all the original potential energy will be converted to heat. We wish that the water temperature rises 5 degrees Celsius. What should be the h value? Okay, the original potential energy difference is delta E equals mgh. And it will turn to heat through the expression delta E equals mc delta T. So, mgh equals mc delta T, and we find that h equals c delta T over g. We saw that the liquid water specific heat is C equals 1 calorie per gram per degree Celsius, equals 4.18 joules per gram per degree Celsius, equals 4,180 joules per kilogram per degree Celsius. So H equals 4,180 times 5 over 10, 2,090 meters. 2,090 meters. All this for 5 degrees Celsius. It's quite a height. And so we have seen the first 4 fluid physical properties. So far, so good. In the next video, we'll talk about viscosity and surface tension. No rush, in a very smooth way. Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.